Kevin Noertker is the co-founder and CEO of Ampair, a pioneer in hybrid electric aviation. Prior to founding Ampair, Kevin served as a senior systems engineer at Northrop Grumman Electric Systems, working on satellite programs. Among other accomplishments, he has led a team that developed a hardware fix for a key component of the Joint Polar Satellite System, improving hurricane projections from 3 days to 5 to 7 days. As an undergraduate research fellow, he investigated requirements for a unique robot capable of collecting rock samples and challenging terrain on Mars, Titan, and the Moon. Please join me in welcoming Kevin to the stage.
Thank you for the introduction. It's a pleasure to be here. I'm Kevin Noertker. As Dana mentioned, I'm co-founder and CEO of a company named Ampair, working on hybrid electric aircraft. We recently joined forces with an organization called Surf Air Mobility to look at this broader ecosystem for the next generation of aviation. You know, Bruce brought up a lot of really good points in the last presentation, talking about the challenges that we have as an industry, where we aspire to go going forward, how we aspire to upgrade our systems, incorporate new technologies, and to do so to improve the safety of the aircraft and of people who are flying in them, of the communities around us, how to improve the economics of the industry, how to decrease the cost of a plane or the cost of operation, how to service more airports. Now, over the next few minutes, I hope to share a part of that solution and how the work that we're doing at Ampair and at Surf Air Mobility can help build a better future for aviation. So we are building the regional air travel ecosystem that sustainably connects the world's communities. I don't know where everybody here traveled in from. I came in from Los Angeles last night. It's about an hour, 15-minute flight, really quick, really easy, except that it took about 5.5 hours of travel time. Flying is not fast anymore. The challenge with especially traveling these type of regional routes, though it was relatively economical, it's about $160 round trip for the ticket. It took 5.5 hours. Now, had I left from home and driven here, it would have taken about 5.5 hours. So I'm not really saving any time. So why do we fly? Well, I fly apparently to put carbon emissions into the environment, because that's a big negative impact that we see in aviation. Now, so what can we do to improve this? I certainly can't charter a plane. That's far too expensive. I can't justify flying on a plane that's got less than 250 people on it, because that's too expensive as well. Something needs to fundamentally shift, and this is really what we're looking at. How do we build a full ecosystem, whether it's the technology of the vehicles or the aggregation of passengers or the operation efficiently of regional airlines? How do we solve many of these problems together? So let's start looking at some of the big challenges in our industry. So currently 3% of global greenhouse gas emissions are emitted each year by aviation. This is on track to double as an industry by 2050, and relative to reductions in emissions in other industries, we're looking at a significant increase. A UK report was suggesting that aviation could be responsible for over 20% of global greenhouse gas emissions by, I think it was the 2050 mark. Now we need to do something to change that. Now the regional flights, this is defined in our world as under 500 miles, account for about 40% of those emissions. So affordable, sustainable flying is enabling this emergence of a new market that serves at a lower price point, at a more sustainable operation, serves a growing demand that we see around us. Now, looking at some of the data, 8 out of 10 people expect that organizations have a focus on sustainability, and 9 out of 10 believe that it's important to do things that are beneficial for the environment. However, only about 50% think that they would choose inconvenience over just the convenience of the status quo. So something needs to change other than just a desire to do well for the world around us. So this is what we, 5 years ago, founded a company to work on, to take the advanced technology that we see in our Teslas or our Priuses or the large number of other electric and hybrid electric vehicles out there, and to see how can these apply safely into aircraft, and what could the impact be. So we started development in early 2016. We had our first flight of what at the time was the world's largest hybrid electric airplane, an upgrade of a Cessna Skymaster. I don't know if anybody remembers the Cessna Skymasters. It's the 337. Some people call it a Mixmaster. So we're mixing it up once again, pulling out that rear engine, putting in a fully electric drivetrain, and enabling the plane to fly with a balance between a combustion system and an electric system. We've worked closely with some really amazing partners. We've worked with NASA. We've worked with the Department of Energy and called ARPA-E, their Advanced Research Projects Agency. We've also, of course, coordinated closely with the FAA and regulatory bodies around the world. So there are a few proof points that we think are really important to talk about. First, by starting with a hybrid electric plane, we are able to mitigate some of the immediate risks that people will identify with electrification. Think about the first electric car that you considered buying and you said, oh boy, where am I going to plug this thing in? I just don't think I'm going to get it because I don't know where the chargers are. I know where my local gas stations are, but I'm just not ready because I don't think I don't believe that I'll be able to plug it in. I'm just too afraid. So we're able to mitigate that with a hybrid electric system, much like a Prius, that doesn't need to plug in everywhere that you go. So actually it's a charge sustaining hybrid. The second thing that you would worry about with your first electric car was how far can it go? Range anxiety. Oh boy, I don't want to have to pull my car off to the side of the road, let alone what do you do if the plane runs out of battery, right? This seems like I mean, we all know when you plan a flight, you make sure you've got sufficient energy, so by process, this is a mitigated risk, but it is something that's still in application. We need to make sure that these vehicles have sufficient range to be able to fly the routes that people need or that airlines need to operate, or even potentially reposition the planes. So we've already demonstrated a flight of over 400 miles. It was 418 miles between Perth and Exeter out in the UK. Longest flight here in the United States was repositioning between Los Angeles and San Francisco, about 350 miles. So we have the endurance and the range for these planes. Longest flight over 3 hours. Now, this is because we're beginning with this pragmatic approach, hybrid electric technology. So let's look at a little bit of the technology that we're incorporating. So electric vehicles, connected vehicles, this digital twin, this predictive maintenance, all of these things that we can see with our Teslas or what we expect from a modern vehicle, but that we really don't get with aircraft that were manufactured decades ago. We're now able to incorporate these into these new planes. A more digital system enabling logging of significant amounts of data of the health of each system, of vibrations within the system, ensuring that every component you can track the health according to the manufacturer's standards, so that when you have degradation, you can actually predictably pull that part out, upgrade it, maintain it, and ensure that you have safe operations. So it's not reactive, it's very proactive in these systems. One of the things that we also see are the technology that we're incorporating. We saw the great borescope picture from the piston engine. There are no pistons in an electric machine. Actually, a motor has only one moving part, really. Taking an engine with hundreds, potentially thousands of moving parts, and simplifying that down to just one brushless motor that has nearly no maintenance other than the bearings that are inside, we're able to significantly improve the reliability of these components. We're able to decrease the cost of maintenance. Now, all these things need to be proven, right? We're not just going to take it at the engineer's word, but we need to prove and certainly expect that the cost to maintain will go down, the frequency of intervals for inspections will ultimately extend, and all to drive toward a more a safer and more reliable system overall. We've demonstrated this in our existing aircraft. We had 100% dispatch reliability over the, it's probably 70 or 80 flights now with this vehicle. Every time we intend to fly, our system's ready to go. There's never been a single time that the electric vehicle systems here, whether it's the batteries, the electronics, the motors, it's always been 100% uptime. Now just imagine if you were operating a fleet of vehicles and you didn't have any downtime because of unforeseen maintenance. That's pretty powerful when you think about the number of vehicles that have to be in a fleet and the cost of operating them. And then finally, I'll touch on one of the reasons that we look at operating and switching over to a hybrid electric plane and eventually a more electric and fully electric plane is really the reduced direct operating costs. So where we're currently operating today, we've measured 31% fuel savings on the same routes. I'll mention this in a slide later, but we deployed our plane to Hawaii as well as into some airline routes in the UK, operating on what is an essential air service route. Now we're in experimental market survey, so no paying customers on our flights. But on that exact same route, operated multiple round trips per day, 31% fuel savings. For an airline, they can spend up to 50% of their operating costs. Generally between 35 and 50% of an airline's total budget is going to fuel. So just imagine if you could save 30% of 50% of your budget. 15% savings is massive. I mean, airlines are scraping for fractions of a percent savings. So big economic impact that we're driving toward. So we're not just talking about this, we're actually working closely with our customers. We believe that you can't solve these problems just in a lab or in theory or in digital models on a computer, but we actually need to go out and do the deeds in the world that we hope to achieve. So we've been deploying our plane with our customers on these market survey flights, flying in Hawaii and, as I mentioned, in Scotland. Really tremendous to actually go and visit these places, particularly because for many of these communities, aviation is a lifeline. We talked about all these regional airports and the convenience of if those airports have service and the inconvenience of if those airports get shut down. In LA, one of our regional airports, Santa Monica, is getting shut down because the community believes that it's more valuable as a park than it is as an airport. And I think that that's a shame. They complain about pollution, they complain about noise, emissions, and I think that this is a trend which we can change. We can make these airports and the industry as a whole seen as a benefit rather than a burden to communities. So at Amp Air and Surf Air Mobility, we're taking, as we see, the lowest risk approach to incorporating advanced technology into aviation. A fundamentally risk-averse industry, we need to make sure that we're doing everything correctly along the way, ensuring that we maintain the trust of the industry and that the performance of our vehicles matches to the high expectations. So first and foremost, we're upgrading airplanes. We're not going out with clean sheet design, urban air mobility, electric vertical takeoff and landing planes. We're upgrading existing planes where the airframe is known, understood, trusted, where the type certificate is still well established, where production is already demonstrated by the OEMs, and where we can take those turbine engines, which are very expensive to operate, or those piston engines, which might be higher cost to maintain, and we can upgrade those existing planes to hybrid electric and eventually fully electric. So this is a low-risk approach to certifying new technology in the industry. And we're also taking a methodical approach to applying the new technology. And here on the slide, I've given a quick example of, for example, battery technology. This is generally where people first think when they go, okay, electric vehicle, lithium-ion batteries. Didn't I see that picture of that Tesla that got on fire? Isn't this dangerous? How could it possibly be applicable? You also think how quickly technology changes, where you say, well, the batteries from 5 years ago are far lower performance than the batteries that we could buy today. How can you possibly integrate a system like a battery into a plane that'll last 40 years? Where that battery is going to be obsolete in 3. Now, our fuel doesn't go obsolete generally. But how do you handle this obsolescence? Well, so this is right in this approach for upgrading planes and building out processes and managing risks that oftentimes our industry really hasn't had to manage. When was the last time you had a 3-year upgrade of a system to the plane? How did you actually manage that STC, the certification, the insurance of these higher performance processes and parts? So with lithium-ion batteries, where we currently are, the energy density, so that's the amount of energy per unit weight, that energy density is the key metric for ensuring that you have the range or endurance that you need. So currently we're at about 200 watt-hours per kilogram for lithium-ion batteries. Now that's all right. That's good enough for our launch products, for the hybrids, not really good enough for a compelling fully electric vehicle. But as we go, and we think on about a 3-year cycle, we'll be able to deploy new batteries to our customers to improve the performance, to advance lithium-ion batteries, or it's kind of a generation 3, which would be around 300 watt-hours per kilogram. We think by the end of the decade, we may have production on cells of advanced solid-state batteries. So this is again a step in front of the current generation of lithium-ion batteries, improving the performance of these planes. But the relevance here is that this is going to be very dynamic, that this new technology comes with the risks of change over time, and that we need as a community to be able to manage those from either the certification or the operation or ultimately the approvals for operation of these planes. So we've been flying that upgraded Cessna SkyMaster. It's really exciting, but our first commercial product is even more exciting. So we've got an exclusive relationship with Textron to upgrade the Cessna Grand Caravan. So the Cessna Grand Caravan is a workhorse in this industry. It's also 208B if you use the letters. We're taking this plane, which is the most prolific aircraft in the short-haul regional flights. These, if you went to Hawaii and island hopped, you'd be flying on one of these. Now we're taking this and we're upgrading it to a hybrid electric configuration that can save on both the emissions as well as the fuel and the maintenance. So with this configuration, we're looking at up to about 25% fuel savings. Now that directly reduces the emissions of the operation, but really what we see is most compelling is that this configuration is one where you're able to operate in and out of any airport. You're able to operate at the full range. So let's say you needed to reposition from East Coast to West Coast. You'd be able to do that just like you could with your standard plane, and this all comes with the hybrid electric. But it's just the beginning of what we see as a massive shift in our industry. Not just what we're working on, there are others working on very compelling products. And this is driven by the electrification technology. And really what I'm here to speak about is more generally the way that we think this industry is going to shift. And to ensure that everybody in this audience is just at least peripherally aware of some of the things that are coming down the pipeline. So what begins as an upgraded Cessna SkyMaster or an upgraded Cessna Grand Caravan turns into an upgraded Twin Otter, a 19-passenger plane, or you get up to the ATR size, these regional turboprops, or maybe even to the larger planes, higher performance. You get a Pilatus, a Denali. You get these planes that are emerging, and as this technology proves itself, we anticipate it will touch nearly every aspect of our industry. That the batteries that we prove in Part 23 aircraft may someday find their way onto auxiliary power unit replacements on larger planes. We think that the technology as proven safety in this shorter haul flights is really going to expand and open up a broad market and broad applications that we should all be aware of. It's also going to drive the industry toward a more sustainable future, beginning with first-generation hybrids at about 25% fuel savings, moving toward plug-in hybrids, which you can get about 50% fuel and emission savings, and of course, what we all, at least in sustainability, desire is that fully electric solution where you can have up to 100% direct emissions reduction. Of course, you have to have a clean grid for that to work. So we're building this solution here, finding flexibility between cost, time, and impact in a way that really the industry has never seen. So it needs to be convenient, affordable, and sustainable. This is when talking to customers, what they've mentioned is the most critical aspects for them. Now, digging into each of these, we look at the convenience. This is generally around the time of travel. If you remember that 5.5-hour flight versus a 5.5-hour drive from LA here, we should be able to do better. We should be able to have a faster travel between, especially with the smaller size planes, flying between the regional airports. The airport that is closer to my home and where our office is located, Hawthorne, rather than going all the way through all of LAX, or landing to the other of the 5,000 airports that were mentioned earlier. Now, cheaper flights. This has been really challenging for existing technology. A turbine engine just costs a lot to operate. And so there hasn't been a way, and sustainable aviation fuel is particularly expensive too, there hasn't been a way to unlock this economics. But when you switch over to electric, you're reducing the fuel burn. You actually do reduce the cost of operation pretty significantly. With a reduced operating cost, reduced maintenance cost, reduced aircraft overall total cost of ownership, now all of a sudden we can reverse that cycle which has been atrophying our industry for decades. We can increase the number of planes that are built, increase the number of planes that are operated, and ultimately decrease the cost of operation. And then finally, as I've mentioned numerous times, I believe in a sustainable solution for aviation. So we're very serious about bringing this to market, not just at the aircraft level, but looking at what would a route network look like for launching these products. Now we've got the route network planner who helped with JetBlue and launching Virgin America, looking not just at where are people flying today, but where are people traveling today? How do we move people who have given up on aviation because it's simply not convenient enough? It probably would have been more convenient for me to drive here than to fly here. Why does that have to be the case? Well, in order to really address this pain point in our industry, we think we need to take a bottoms-up, looking at where customers want to go to and from, and to connect those point-to-point routes in a very economical way. And though I showed a network example in California where we're based, this is all over the country. 5,000 airports. There are actually, I think, 14,000 places that you could possibly land in the United States. 5,000 where you could fly commercially, yet 70% of airline traffic goes through just 30 airports. So that leaves just about 4,970 airports that aren't getting service. What a waste of infrastructure. How can we possibly justify that? Well, no wonder the airports are getting shut down, because nobody's flying to them. It's not profitable. There's no commercial service. It's all just private, wealthy business jets. But how can we change that? And this is really what we're looking at. How do we take the infrastructure that exists in the United States and enable people to use it? And so this requires an ecosystem solution that we collectively need to prepare for these changes. I've touched on a few of them. Obviously we have infrastructure, the airports, the charging infrastructure, the grid, the electricity grid, local governments as well as at the federal level. We have aircraft financing that needs to come into play, as well as, of course, our operators and the insurance, and how do you handle the liabilities of bringing new technology to market. We don't pretend to have all of the answers, but we certainly are the ones that are driving the conversations. And so what I encourage everybody to do is, if you're interested in learning more about the details, ask questions while I'm up here on stage, and find me later in this event, and I'll be happy to talk to you about what's coming down the pipeline. So thank you. Do you have any questions? All right, well, I think next up, oh, we've got one right over here.
You might have mentioned this. If you did, I apologize, I didn't hear it. So how long does it take to recharge after a flight? You know, what's the downtime?
So the launch product, that Cessna Grand Caravan, is what's called a charge-sustaining hybrid. It's like a Toyota Prius.
Okay.
So you don't have, the first generation of Toyota Priuses didn't have to plug in, right? So they saved a little bit of fuel by managing the peak energy usage, but they didn't have to charge. There was zero downtime for charging. It's just refueling, just like any other car. Similarly, our launch product is going to be a charge-sustaining hybrid where you don't have that downtime. Now, more electric versions, like the current Prius you could buy, you can plug in. Or similarly, if you bought a fully electric variant of a car, you have the multiple tiers of charging. In those cases, we're looking at maintaining turnaround times on the order of about 30 minutes. Most of our customers, especially if they're carrying passengers, are looking for 15 to 30-minute turnaround. If you're flying cargo, it's a little bit different, and we might be able to do longer turnarounds for them. But to specifically answer the question, it's no charging on the first launch product. Yeah.
What kind of engine is it? So you're replacing turbine engines in some cases. So what kind of engine?
So it's we use an electric motor connected to the power electronics, which condition the power to turn the motor as you desire, a lithium-ion battery pack. And then there are, for the generator, there are two options that go into the planes. The one we'll be launching with turbo generator. So this is a turbine core connected to a generator, like an electric machine that generates the power.
So it's the electric motor is actually doing the propulsion part, and the...
That's correct. That's correct, yeah. And so if you think about it, you have redundant sources of power. The electric motor itself is very reliable. The power electronics themselves are also very reliable. So the way we think about the architecture and for specifically redundancy purposes, you can fly the plane fully on the battery pack. You could also fly the plane fully on the generator. Now, at degraded power, but definitely within the realm of controllability. So for example, and this a slightly different architecture that we're flying in the Cessna Skymaster, where that's actually a twin engine, one fully electric, one fully combustion. During our engineering flight tests, we would shut off one or the other and be able to fully operate the aircraft no problem. And we think that this is a type of redundancy that will actually improve the safety of a vehicle, that even a single engine Cessna Grand Caravan has twin engine reliability, at least in a degraded performance. Yep. Oh, we've got one in the back. Yeah, great question. So the question was, is our intention to go fully electric? And if so, what are our considerations around the infrastructure, specifically charging infrastructure? Yes, our intention is to go fully electric. If the batteries were good enough today, that's where we would go. Some of our colleagues at other companies in the industry are blindly driving just toward that electric future, and someday they will deliver a useful product fully electric, just like we will. We believe that the first step being hybrid, just like we see today. A hybrid can always drive further than its fully electric counterpart. We think similarly, a hybrid electric plane will have higher performance, longer range, higher passenger capability than the fully electric. Now, one of the reasons we've gone with this charge-sustaining hybrid approach is because charging infrastructure is something that keeps me up at night. It also kept up every electric vehicle owner, probably still today. People think about, okay, where am I going to charge? Am I going to really have to put one in my garage? Where are the charging stations available? At these 5,000 airports, are we really going to upgrade them for charging? And even if you did, a lot of these are very rural places where the grid can't even handle a supercharger for one plane, let alone a fleet. So do you need battery backup? Do you need local generation and storage? Like, this is a hard problem. It's a problem that will be solved step by step and incrementally. We will fix it eventually, but it will take time. And that's why we're beginning in this staged approach, where starting with a charge-sustaining hybrid that is provisioned for plug-in, if you land at an airport and you have the time and the capacity and the grid to charge the plane, you do. And if you're operating to airports that don't yet have that capability, then you're still operating just fine. And we think that this is a way to thoughtfully expand that infrastructure, specifically the charging infrastructure, to the high-frequency airports where it's known and needed and the demand can be justified, so you can justify economically the investment into the infrastructure along the way. And then eventually, give us a few decades, many or most of the airports will have that infrastructure available. Yep.
How do you solve problems such as pneumatics or bleed air that are typical in turbine engines?
So with the hybrid approach, we're able to take bleed air off of the core that we're operating with. So that is the baseline. In a fully electric, it's a bit tougher. Like, how do you handle pitch control on your propeller? And there are a number of solutions. Sometimes they're parasitic, like just adding an extra pump in order to get the pressure that you need, or adding environmental control systems, right? Managing call it the temperature of the cabin and others. These are things that generally had relied on the engine. And what it really means is that we just have to sap power from our own system, pull extra power out of the battery in order to power these auxiliary systems as well. And that's really what the approach is. But yeah, that's one of the down in the details challenges that when you really get into the engineering, it's got to solve. All right, well, I won't keep us from coffee anymore. Thank you all for your time. Take care.